Hey, uh, welcome everyone. So in this session, we will take an example of how integral calculus is helpful in solving a real world problem. So what we'll do is we will try to find the volume of a regular solid like a cone. We'll try to derive the formula of volume of a cone by using integral calculus. Now, as a base on which we'll do this derivation, first we will look at the volume of a cylinder. Okay. So we know that a cylinder of radius r and height h, it has a volume pi r square h. Okay. Now, just to illustrate the idea of how we would use integral calculus for a cone, first we will apply the same idea on cylinder, which is a simpler solid compared to a cone. Okay. Why is it simpler? That's because its radius and its height are uniform throughout throughout the body, unlike a cone where the radius keeps changing with height. Now, the way to apply integral calculus to find the volume of a cylinder like this is that first we take a small slice in this cylinder. So the small slice will also be a cylinder. It will be like a minuscule cylinder, and its height will be the small h. The reason I'm using small h instead of capital H here is because capital H is a fixed height, whereas the small height that we are taking, we are going to take all these small cylinders and stack on top of each other. So we'll take, we'll denote this height as a d small h. Okay. So what we now the volume of this small cylinder is pi into r square into dh. Now, to find the volume of the total cylinder, we have to integrate this between the limits 0 and capital H. So that gives you pi into r square into h, the volume with limit going from 0 to h. And if you apply upper limit minus lower limit, which is h minus 0, which is capital H, it gives you pi into r square into capital H, which is the volume of the cylinder. Now we will apply this idea to derive the volume of cone. Okay, so right now to find the volume of cone, what we'll do is we'll take a cone. For the sake of clarity, we'll invert this cone. And we know that the radius of a cone is r, and its height is capital H. Okay. Now we have to take a small slice in this cone, find the volume of it, and then integrate it over the whole height so that it will give the full volume of the cone. Now, how will we do it? You take a small slice. Let's say its radius at this point is small r, and let's say this is at a height of small h. Now let's say that the height of this specific slice is dh. Okay. Now this small slice dh height, this actually behaves. This small slice behaves like a cylinder because the height is so small that you don't see the tapering that you would see in the larger cone. Okay. So this segment or section with the height dh is actually a cylinder with radius small r and a height dh. And the volume of this small slice is pi small r square dh. Okay. Now to integrate this pi r square small d small h, we need to incorporate into this equation or this expression we need to incorporate into this expression the variation of radius with respect to height. As you can see, at the top or a height h, the radius is r, and when the height becomes 0, the radius drops to 0. Okay, so the way you would approach this is at a height h, the radius is r, and at a height h, what is the radius? So that will be h by h into r. That is the small r. Okay, so just to restate this, what we're doing is finding the radius at any given height after knowing that at a height of h, the radius drops from r to 0. So with that understanding, we find the expression for small r, and then we incorporate this expression number 2 into expression number 1. So we get pi into h square r square by capital H square into dh as the volume of the small slice. Now, to find the volume of the whole cone, we are going to integrate this from a height going from 0 to capital H. So this becomes pi r square by capital H square integral small h square d small h, height going from 0 to capital H. Okay, now I'm going to continue here. If you integrate h square dh, it is h cubed by 3. That's the formula of integral h square dh. So that becomes pi into r square divided by h square into h cubed by 3 with limits applied from 0 to capital H. So that gives you pi r square capital H square into h cubed by 3, which is 1 by 3 pi r square h, which is the volume of the cone. Now, beyond this, what is the practical use of integral calculus? Now, let's consider an irregular solid. Okay. Okay. Let's consider an irregular solid like this. Now, to find the volume of this, what you have to do is split this into partitions. And for each of the partitions, find the expression f of x, which will give you the map of that partition, and then integrate each of them and then add them up. That will give you the volume of an irregular solid like this. So this is one practical use of integral calculus. I hope this small session was useful to you, and I hope you enjoyed it. Thank you for watching.